So we're looking for the force of gravity acting on a 70 kilogram astronaut, which is 1.5 RE above the surface of the Earth. This thing right here, RE is, I couldn't figure out how to get a subscript, but it's actually R little e, and that is 1.5 times the radius of the Earth. So let's see if I can make this RE, there we go. Okay, so what we're picturing is something like this. We've got the Earth is kind of here. We've got our Death Star up here. The Death Star, in case you don't know, is from Star Wars. It's a nice big ship. Anyways, if this is the Earth, and you can picture the Earth kind of coming around like this, here is the radius of the Earth. That is RE. We're told that we're 1.5 RE radius of the Earth above the surface of the Earth. This is 1.5 RE. That's his RE. I keep having trouble with my E's here today. See if I can get this. RE. There we go. If we're 1.5 radii above the Earth, then this whole distance from the center of the Earth to the center of the Death Star is 1 RE plus 1.5 RE. That's actually 2.5 RE. Okay, so just keep that in mind as we do this. That number is going to come up again. Something to note, on Earth, so let's start off looking here on Earth. If I'm looking on Earth, I know that the weight of anything is mass times little g, where little g is 9.8. So Fg is the mass of this astronaut, 70 kilograms, times 9.8. We can work that out, and we can find out this astronaut on Earth weighs 686 newtons. I'm going to call that my position 1. So I'm going to say right here, there's position 1. And I'm going to say up here at this new spot that we're looking at, that's position 2. So on Earth, I'm going to call this F1. You could call it FG1 if you want. That's 686 newtons. And I know that the distance that I am is 1 Earth radius. Here at position 1, so like right over here, if I'm at position 1, I am 1 Earth radius away. Okay, so there's a couple things. These aren't answers. These are just some things I'm going to need to know. In space, let's go over here and say in space, those numbers aren't quite the same. What we're looking for is, what is F2? This is force of gravity 2. This is the weight way up here when I'm on the Death Star. But I do know distance 2. Distance 2, this is what we talked about before right here. Distance 2 is this whole thing. The spaceship, or the Death Star, or whatever, the astronaut inside there, is 2.5 RE. And we're going to need that thing, D2, in order to solve for F2. The equation that I've got then is this thing. It is F2 over F1, and that's equal to D1 squared over D2 squared. We could rearrange that and solve for F2. We could say F2 then is equal to, if I bring F1, kind of cross multiply up here, F1 times D1 squared over D2 squared. Now we can just sub in all of our numbers. We know what F2 is. Sorry, we don't know what F2 is. We know what F1 is. This is 686. D1 is RE. And don't forget, D1 is squared. And D2 is 2.5 RE squared. So 2.5 RE squared. Don't forget, it's not just the RE that's squared, it's the 2.5 that's squared as well. So this top RE squared can cancel out with this RE squared, but I still have 2.5 squared. So this is F2 is equal to 686 divided by 2.5 squared. And I'll come right over here. And then over here we can say F2 then is equal to 110 newtons, approximately. It's 109.8, I think, something like that. And that is the astronaut's weight when they're on the Death Star, which is 1.5 RE above the surface of the Earth. Okay, so similar to the last question, we've got something like, let's see, the Earth. Oh, where's my pen? There we go. The Earth is down here. Somewhere up here, we've got our International Space Station. Here is F2, that's the weight of whatever it is. Down here, we're going to be looking for F1. So there's position 2 at the top, position 1 at the bottom. We also know something about, here's the radius of the Earth again. And then this distance right here, we're told this time is 300 kilometers. That distance. We were given the radius of the Earth as well, 6,400 kilometers. Similar to what we did last time, we're going to look on Earth. So you could say this is like position 1. I'll say on Earth here. On the Earth, we're going to try to find the weight of this astronaut. And again, just like last time, we know the weight of anything is just its mass. In this case, it's 80 kilograms times 9.8. So the astronaut's weight on Earth, 784 newtons. And like we said over in the picture right over here, this is going to be my F1. So this is their weight at position 1, 784 newtons. I also know D1, so kind of like last time, D1 is just this thing here. If I'm at position 1 on the surface of the Earth, then D1 is just the radius of the Earth. I'm going to go ahead and make this into meters, though. I don't like kilometers. It's not the standard base unit. So that stuff is true on the Earth. Then we can also say, what about in space? So again, kind of like last time. A little dotted line down here. Here we're going to talk about in space. In space, I don't know F2. That's what I'm looking for. The force of gravity acting on this 80 kilogram astronaut in space, his weight in space or her weight in space. So that thing's a question mark. I do know D2 though. Remember, D2 is the distance between the astronaut and the center of the Earth. So way up here is the astronaut, way down here is the center of the Earth. It's this entire distance. Okay, so to find that thing, we're going to have to say this is the radius of the Earth plus our 300. It doesn't look much like a 300. Here we go. 300, and don't forget that's kilometers. Again, I want to convert that thing into meters. D2 then is 6,400,000 plus this 300 kilometers is 300,000 meters. Okay, so D2, let's see, that is, let's use some scientific notation here. 6.7 times 10 to the 6 meters. Okay, so there's D2. I'm looking for F2. I'm looking for this thing up here. So similar to what we did before, we're going to say F2 over F1 is equal to D1 squared over D2 squared. F2 is what I'm looking for. I'm just going to go ahead and sub in this time. F2. F1 was 784. D1, full radius of the Earth, 6.4 times 10 to the 6. And don't forget that's squared. And that's divided by D2, 6.7 times 10 to the 6. And again, don't forget that's all squared. If I can come up here, When I divide those things, I'm going to have to end up multiplying by 784. If I solve for F2, that's about 715 newtons, approximately. For significant digits, I guess we should actually round that a little bit. Where's my eraser? Here it is. Oh, it's not going to let me erase this time. Anyways, for significant digits, we should say it's about 720 newtons, you could say, or 7.2 times 10 to the 3. And there is my answer. And I'll see if I can squeeze B just over here. Let's go with a different color here for some white. Here's part B. We know FG is just mg. We know the person's weight. So the person's weight, I'll use the unrounded value. It's 715. It was actually 715.4 approximately. We know that the astronaut's mass is 80. We're going to multiply that by g. That's what we're going to try to find. What's the gravitational field strength up there? Remember, on Earth it's 9.8. Here it's not going to be 9.8. We can divide both sides by 80. And then we can solve for little g and get little g is about 8.9 meters per second squared. And that is the gravitational field strength on the International Space Station. So when we're doing these questions, all we need to do to use this formula here, we need to get 3 out of those 4 variables. Typically, we know F1, D1, and then D2, we're going to solve for force. It doesn't have to be that way. It can be any combination of those things.